Rational functions. In the previous sections, we have built polynomials based on the positive whole number power functions. In this section, we explore functions based on power functions with negative integer powers called rational functions. Example 1. You plan to drive 100 miles. Find a formula for the time the trip will take as a function of the speed you drive. You may recall that multiplying speed by time will give you distance. If we let t represent the drive time in hours and v represent the velocity, speed, or rate at which we drive, then v multiplied by t equals distance. Since our distances is fixed at 100 miles, vt equals 100. So solving this relationship for the time gives us the function we desired. T of v equals 100 divided by v equals 100 v to the negative 1 power. While this type of relationship can be written using the negative exponent, it is more common to see it written as a fraction. This particular example is one of an inversely proportional relationship where one quantity is a constant divided by the other quantity, like y equals 5 divided by x. Notice that this is a transformation of the reciprocal toolkit function, f of x equals 1 over x. Several natural phenomena, such as gravitational force and volume of sound, behave in a manner inversely proportional to the square of another quantity. For example, the volume v of a sound heard at a distance d from the source would be related by v equals k divided by d squared for some constant value k. These functions are transformations of the reciprocal squared toolkit function f of x equals 1 over x squared. We have seen the graphs of the basic reciprocal function and the squared reciprocal function from our study of toolkit functions. These graphs have several important features. Let's begin by looking at the reciprocal function. F of x equals 1 over x. As you well know, dividing by 0 is not allowed, and therefore 0 is not in the domain. And so the function is undefined at an input of 0. Short run behavior. As the input values approach 0 from the left side, taking on very small negative values, the function values become very large in the negative direction. In other words, they approach negative infinity. We write, as x approaches 0 to the negative power, f of x approaches negative infinity. As we approach 0 from the right side, small positive input values, the function values become very large in the positive direction, approaching infinity. We write, as x approaches 0 to the positive power, f of x approaches infinity. This behavior creates a vertical asymptote. An asymptote is a line that the graph approaches. In this case, the graph is approaching the vertical line x equals 0 as the input becomes close to 0. Long run behavior. As the values of x approach infinity, the function values approach 0. As the values of x approach negative infinity, the function values approach 0. Symbolically, as x approaches positive or negative infinity, f of x approaches 0. Based on this long-run behavior in the graph, we can see that the function approaches 0, but never actually reaches 0. It just levels off as the inputs become large. This behavior creates a horizontal asymptote. In this case, the graph is approaching the horizontal line f of x equals 0 as the input becomes very large in the negative and positive directions. Vertical and horizontal asymptotes. A vertical asymptote of a graph is a vertical line x equals a where the graph tends towards positive or negative infinity as the inputs approach a. As x approaches a, f of x approaches positive or negative infinity. A horizontal asymptote of a graph is a horizontal line y equals b where the graph approaches the line as the inputs get large. As x approaches positive or negative infinity, f of x approaches b. Try it now. Use symbolic notation to describe the long-run behavior and short-run behavior for the reciprocal squared function. Example 2. Sketch a graph of the reciprocal function shifted 2 units to the left and 3 units. Identify the horizontal and vertical asymptotes of the graph, if any. Transforming the graph left 2 and up 3 would result in the function f of x equals 1 divided by x plus 2 plus 3, or equivalently by giving the terms a common denominator, f of x equals 3x plus 7 divided by x plus 2. Shifting the toolkit function would give us this graph. Notice that this equation is undefined at x equals -2, and the graph also is showing a vertical asymptote at x equals -2. As x approaches -2 to the negative power, f of x approaches negative infinity, and as x approaches -2 to the positive power, f of x approaches infinity. As the inputs grow large, the graph appears to be leveling off at output values of 3, indicating a horizontal asymptote at y equals 3. As x approaches positive or negative infinity, f of x approaches 3. Notice that horizontal and vertical asymptotes get shifted left 2 and up 3 along with the function. Try it now. Sketch the graph and find the horizontal and vertical asymptotes of the reciprocal squared function that has been shifted right 3 units and down 4 units. In the previous example, we shifted a toolkit function in a way that resulted in a function of the form f of x equals 3x plus 7 divided by x plus 2. This is an example of a more general rational function. Rational function. A rational function is a function that can be written as the ratio of 2 polynomials, p of x and q of x. F of x equals p of x divided by q of x equals a sub 0 plus a sub 1 x plus a sub 2 x squared plus and so on plus a sub p x to the p power divided by b sub 0 plus b sub 1 x plus b sub 2 x squared plus and so on plus b sub q x to the q power. Example 3. A large mixing tank currently contains 100 gallons of water into which 5 pounds of sugar have been mixed. A tap will open, pouring 10 gallons per minute of water into the tank at the same time sugar is poured into the tank at a rate of 1 pound per minute. Find the concentration, pounds per gallon, of sugar in the tank after t minutes. Notice that the amount of water in the tank is changing linearly, as is the amount of sugar in the tank. We can write an equation independently for each. Water equals 100 plus 10t. Sugar equals 5 plus 1t. The concentration, C, will be the ratio of pounds of sugar to gallons of water. C of t equals 5 plus t divided by 100 plus 10t. Finding asymptotes and intercepts. Given a rational function, as part of investigating the short-run behavior, we are interested in finding any vertical and horizontal asymptotes, as well as finding any vertical or horizontal intercepts, as we have done in the past. To find vertical asymptotes, we notice that the vertical asymptotes in our examples occur when the denominator is 0, so the function is undefined. With one exception, a vertical asymptote will occur whenever the denominator is 0. Example 4. Find the vertical asymptotes of the function k of x equals 5 plus 2x squared divided by 2 minus x squared. To find the vertical asymptotes, we determine where this function will be undefined by setting the denominator equal to 0. 2 minus x squared equals 0. 2 plus x multiplied by 1 minus x equals 0. X equals -2, 1. Example 5. Find the vertical asymptotes of the function k of x equals x minus 2 divided by x squared minus 4. To find the vertical asymptotes, we determine where this function will be undefined by finding where denominator will be 0. We can do this by factoring k of x equals x minus 2 divided by x squared minus 4 equals x minus 2 divided by x minus 2 multiplied by x plus 2. So the denominator is 0 at x equals 2 or negative 2. However, the numerator of this function is also equal to 0 when x equals 2. The function will still be undefined at 2 since 0 divided by 0 is undefined, but if x does not equal 2, then x minus 2 divided by x minus 2 multiplied by x plus 2 equals 1 over x plus 2, which does not have a vertical asymptote at x equals 2. The graph of k of x will have a vertical asymptote at x equals negative 2, but at x equals 2, the graph will have a hole, a single point where the graph is not defined, indicated by an open circle.